y goes to y of s. That's what you want me to do, isn't it? Okay, right. Let's do it. We want the Laplace transform. Okay, that's the Laplace transform dy dt, isn't it? This is the Laplace transform of y. As you might imagine, I'm not going to do all the details. But if it was a first year maths thing, or if it was a maths A-level question, and you saw something like that, what integral technique would immediately jump to mind? It's by parts. So you obviously write that, what would you do? dy dt equals du, and you write e to the minus st equals v, and you put the parts form in, you crank it, and it comes out like that. That's all there is to it. I mean, the stuff is just technical detail. That's how you do it. It's very simple by parts. And you obviously you're going to get something like, you're going to get u at 0. Okay, coming in as all the limit things on here, aren't you? And that's where that's y rather. That would be y naught, and that's where the y naught term comes from. Very simply. Obviously, when you differentiate this to get dv, you get the s in front of it. So the steps are very trivial. You could do that in 5 minutes. So that's how you prove it. And to do it more than once, you just repeat the process. I haven't proved most of the Laplace transform properties because I don't ask you whether to do that in the exam, so there's not much point in going through it. Any other questions? Yes?
When we describe like the pole plot, do the zeros matter at all? Do you have to talk about what they do?
Oh, well, let's give you an example. And that's equivalent to, which is equivalent to 1 over s plus 1 minus 1 over s plus 2. Okay? Right? That's two first order systems, isn't it? They're actually in parallel. I said in series before, they're actually in parallel. 1 over s plus 1, 1 over s plus 2. That's equivalent to the overall system. The poles set the behaviour. What do the zeros do? They tell you how big each of these contributions is. Now, they're not trivial, but what they don't tell you is about the basic dynamics of the system. Is it heavily damped, lightly damped, stable, or unstable? That's why I say it's the poles that characterise the system. They obviously have numerical effects. If this was 3, then we'd have 3 out here, wouldn't we? Things like this, whatever.
But when we're talking about
Or if it was s plus a, s plus 1, you can do that for yourselves, but it will be a and b, whatever that comes out as. Okay? And that tells you the relative contributions, the bits from each pole. Now, they're not trivial. They're used in design, but they do not tell you important things like, is it heavily, is it lightly damped, is it stable or unstable? These are key characteristics of the system, and I think this example shows all that. Okay, next question. Yeah?
When it comes to an Argand diagram, if there's stuff on the numerator apart from 1, does that affect it at all? Or?
No, I mean, if it was 3, or I said, what I suggested you did a few minutes ago, this is the pole plot for this system, you just put times 3, like something like that. That's a full description. As I say, how big the output is, because y of s is equal to h of s, u of s. So if it's times by 3, the output's 3 times bigger, isn't it? So it's basically the scale of the whole thing, but it doesn't affect the dynamics and the details of how it shapes, but it does affect how big it is. That's why it's sometimes called the gain of the system. Next question. Okay, let's push on with this sinusoidally stuff. Now, if you look at this expression, which I'll write it down again, For a very simple case, our simplest case, this is just the u of t is equal to cos omega t, the simplest possible case. We see that it's the size, the magnitude of the transfer frequency response function that really determines what goes on. We get phase shift, but that tells you how big it is or not. So a very important thing to plot is h of j omega, its magnitude, and depending on the type of system, let's take for example this system, where h of j omega is equal to 1 upon omega squared plus 1 squared. Take that as an example. When omega is less than 1, then the thing is just flat and doesn't do very much. It actually has a value of 1. When omega is very large compared to 1, it looks like 1 upon omega. So it obviously tips over at some point, and the value where it tips over around about here, that's omega equal to 1, and this value is 1 upon root 2. So what that system does, it doesn't affect, it passes low frequencies below this critical omega equal to 1, which is defined by the pole of the system. It attenuates things well above the pole, and it sort of bends over around the pole. And this is called a low-pass system. Does anybody know why all systems are low-pass? Whatever the fine details are, in general, in the broad sweep of things, they're low-pass. Does anybody know why? Well, let's take a PA amplifier, right? It passes frequencies from what? A few hertz to about 20 kilohertz, yeah? Does it pass X-ray frequencies, 10 to the 16 hertz? Not really. Good job it doesn't. You wouldn't want a PA system picking up a few X-rays and multiplying by a factor of 10,000 and radiating them out the speakers. That would not be good, would it? Probably a good thing they are. So in general, all systems are by definition low pass. They can have detail on the way. They're going to be stuck here in the what's called the pass band with detail, but in general they're not. Now, a system which is not like that